Alright, so this lesson we are going to be continuing stuff that we kind of already did when we were using limits only instead of doing shortcuts for derivatives. We're going to talk about values of k, or values of constants that will make a function continuous for a piecewise function, which means the two pieces would touch each other. And then values of constants that would make the function differentiable, which means they would touch, but they also have smooth transitions. All right, so let's talk. This first one is just about continuous. So we're going to find the value of k that makes the function continuous everywhere if possible. Now sometimes this is not possible, but for a function to be continuous, we need, at a point, we need the limit as x approaches that point from the left of f of x to equal the limit as x approaches that point from the right of f of x, and that needs to equal f of a. And the main issue with that is that f of a must be defined. All right, and the only thing on these that would make that value undefined is if neither one of these pieces or none of the pieces had an or equal to bar. But this has one, so we're fine. When we go to do this one, it has an or equal to bar, so we're fine on the part of it being undefined. But that is something to check for, because sometimes you'll do like a whole bunch of work, and then in the end there's no way that it would be continuous because that value wasn't defined anymore. So just double check for that or equal to bar and you're good. So this one has the or equal to bar, so I'm just going to go ahead and say that f of 1 is defined. So we're good right here. So what we want to set it up so the left and right hand limits are equal to each other. And so the point in question is 1, where the piece changes from one of the function pieces to the other. So what we want is the limit as x approaches 1 from the left of f of x. I'm going to just go ahead, I'm going to go ahead and use the left piece. And so this one is switched the way it normally is. The left side is when x is less than 1, so I'm just going to go ahead and use that function expression. And we want it to equal the limit as x approaches 1 from the right. And so the right side is when x is greater than 1, so I'll just go ahead and use that function expression. Okay, and then to evaluate these limits, you're just going to take that 1 and you're going to put it in for the x's. Alright, and I'm just going to go ahead and add that 1 over. So we have 1/2 minus 2 plus 1. So negative 2 plus 1 is going to be negative 1. 1/2 minus 1 is going to be negative 1/2. Alright, so we've already made sure that f of 1 is undefined. So we know that if we take this negative 1/2 and we put it right there, those two pieces would touch each other and the function would be continuous. So it would be a line with a slope of 1/2 going here, and then you would have after 1 a line with a slope of negative 1/2 going, so continuous. It wouldn't be differentiable for sure because there's a sharp piece, but that question isn't asking about that. Okay, and then for example 2, we're going to find the value of a and b that make the function differentiable everywhere if possible. So let's start with continuous. Alright, so we already can see that f of 1 is defined because I have this or equal to bar. Alright, so what we want is for the limit as x approaches 1 from the left Then the left side is going to be less than 1, so 3 minus x is equal to the limit as x approaches 1 from the right. And so that's going to be ax squared plus bx. Okay, and I should have said this before. So for a function to be differentiable, must be continuous. So that's what we already did. And also the slopes have to match from the left and right. Okay, so we're going to hold off on that. If the function is not continuous, we don't even mess with that. So we'll start with the continuous. So we'll plug the 1 in. All right, and so we get that 3 minus 1 is equal to a plus b, or 2 is equal to a plus b. So for this function to be continuous, we would have to add a and b to get 2 and get 2. So we don't know what a and b are. So the last one, we immediately, after one step, we knew what k was. We don't have that luxury this time, but that's okay. We can go on to the situation where the slopes must match. And so to make sure the slopes match, we can actually just find the derivative of this piecewise function. And when you find the derivative of a piecewise function, you just take the derivative of each piece. So when we start with the top piece, the derivative of 3 is just 0. And the derivative of negative x is negative 1. And that piece we use when x is less than 1. Okay? And then just remember, when we're doing the derivatives here, it's with respect to x. So a and b are constants. That's what we're looking for. And so when we do the power rule, we're going to multiply by the power and take 1 away. So it would be 2x. All right, and then think of b like a constant. So if we were trying to find the derivative of 2x, that would just be 2. Negative 3x, that would just be negative 3 for the derivative. So the derivative of bx is just b. And we will use that one when x is greater than or equal to 1. All right, so what we want for the slopes to match, we want the limit as x approaches 1 from the left of f prime of x, which the left side is just always going to be negative 1, is going to equal the limit as x approaches 1 from the right of 2x plus b. Now it's been a little while, but when you take the limit of a constant, it's just that constant. And then we'll plug 1 in. Ooh, I messed up. I think I said it, but maybe didn't write it. It's 2ax. So we multiply by that 2, so it would be 2a, and then take 1 away. Okay, so now when I plug in the 1, it's 2a plus b. All right, so what this gives us is a system of equations. And they have the same 2 variables, so 2 equations with the same 2 variables. We can solve them by doing substitution or elimination. I prefer elimination, especially when it's like this one, and I'll show you what I'm talking about in a second. So what if we're going to do elimination, we would line up the a's and the b's, and then because these are the same, all I have to do is just subtract them. So I would do minus, minus, and then when you subtract negative 1, it's a plus. All right, and then that's going to be negative a is equal to 3. So a must be negative 3. So we found our a. All right, and then to find the b that goes with that a, we can put it here, or we can put it here, I'm going to take it, I'm going to put it into the first one. And solve it. B has to be equal to 5. Okay, so if A is negative 3 and B is 5, this function would be differentiable everywhere. Negative 3 and 5. So those two graphs would touch each other, and there would also be some kind of smooth transition. All right, so now you guys are going to do the twinning exercise.